Modern enterprise software systems operate at a staggering scale. Millions of lines of code execute across thousands of servers, handling millions of simultaneous transactions. Designing a system with this level of density exposes a severe communication breakdown among the people responsible for building it. They are looking at the exact same application, but they require entirely different paradigms of information to do their jobs. A software developer examines the system and needs to see the static, structural organization of source code, object classes, and domain concepts. A systems engineer looks at the software, but static code is useless. They need to map dynamic runtime processes, evaluate concurrency, and ensure fault tolerance. A network architect ignores both perspectives. They are solely concerned with how those software components map to physical hardware infrastructure and deployment configurations. A single architectural blueprint cannot capture all of these competing concerns. A schematic detailed enough for a programmer is often unreadable to a network architect. Without a unified framework to translate between these conflicting perspectives, the various specialized blueprints begin to drift, creating structural gaps between the code being written and the hardware being deployed. In 1995, software engineer Philippe Cruchton formalized a solution to this problem: the 4+1 architectural view model. This framework describes complex software from multiple interrelated yet isolated perspectives. Cruchton's 4+1 approach fractures the system into 4 views. The logical view structures abstractions for designers. The process view maps dynamic behavior for analysts. The development view organizes static code for programmers. The physical view dictates hardware deployment for administrators. Isolating these disciplines solves the problem of cluttered, specialized blueprints. But it creates a new vulnerability. 4 isolated teams building separate blueprints lack a central gravitational force to keep their designs from contradicting one another. The solution to that fragmentation is the +1 in the 4+1 framework, the scenarios view. The scenarios view acts as the architectural glue. It forces isolated engineering disciplines to align by illustrating how components must collaborate. It achieves this alignment by ignoring internal technical details entirely. Instead, it focuses strictly on key user requirements and representative interaction sequences. The primary tool used to construct this scenarios view is the UML use case diagram. UML stands for Unified Modeling Language, a standardized visual notation used to communicate system designs consistently. To understand how this diagram anchors an entire software project, we must look at how it gets built from scratch. A completed use case diagram must answer exactly 3 questions. Who is the system for? What must it do? And why build it? It is not a flowchart of internal logic. It is a strict visual contract depicting the system exactly as it appears to the outside world. The first functional step in translating abstract requirements into a unified model is defining what actually belongs to the system. This blank canvas now shows a system boundary. This represents the absolute limits of the software being modeled. By UML rules, this boundary must be represented by a strict rectangular box, clearly separating the interior from the exterior. This geometry forces a necessary binary decision upon the software architect. Every proposed feature must be explicitly placed inside or outside this line. Everything placed inside the box is an internal responsibility. It is code that the developers must build, test, and maintain. Everything outside the box represents the external environment. The system can interact with these external elements, but it cannot control them. Without a rigidly defined boundary, project scope creeps infinitely outward, making architectural alignment completely impossible to achieve. Step 2 is populating that external environment with actors. In UML, an actor is any external entity that interacts across the system boundary. A common misconception is that actors represent literal individuals. They represent specific functional roles. One human user might act as a customer on Monday and an administrator on Tuesday. Because they represent roles, actors are not always human. They are frequently IoT hardware devices, like automated background scripts or external web APIs. Primary actors are active participants. They trigger the system to perform a function and derive a direct benefit from the result. UML dictates a spatial rule for primary actors. They are universally placed on the left side of the system boundary. The second classification is secondary actors. These are passive entities. They do not initiate actions. Instead, they play a supporting role to help the primary actor achieve their goal. An external banking API verifying a credit card or a database administrator receiving an automated log are both secondary actors. The visual rule here is the inverse. Secondary actors are always placed on the right side of the system boundary. By spatially isolating active triggers on the left and passive support on the right, the architect visually locks down all external variables before a single line of internal code is written. Step 3 moves inside the boundary to define the actual functionalities of the system. These are the use cases. Visually, use cases are exclusively represented by ovals, and they must be placed completely inside the system boundary. Logically, each oval represents a specific sequence of actions that yields an observable, valuable result for an actor. UML enforces a strict grammatical rule for naming these functions. They must use a verb-noun format. Titles must be actionable. You cannot use passive nouns. The diagram demands commands like place order, process payment, or update inventory. Once internal functions are named, they are linked to the external world through association lines. Solid lines are drawn connecting the customer on the left to place order and process payment, which then connects to the bank API on the right. These verb-noun ovals finally answer the "what must it do" question, providing the atomic requirements the development team will actually build. Look at this assembled diagram. Its value lies in the strictness of its geometry. Data flows logically across the boundary. Primary actors initiate the action from the left. Internal processing occurs as the system executes the specific verb-noun function contained within the boundary. And resolution happens as the system reaches out to the secondary actors on the right to finalize the transaction. The diagram functions as an operational contract, ensuring every piece of internal system logic is explicitly anchored to a real-world requirement. When we shift back to the macro level, we see exactly how this 2D diagram solves the initial problem of architectural fragmentation. Developers look at this diagram to verify that their static code in the development view actually supports the required use cases. Systems engineers use it to ensure their runtime configurations in the process view can handle the volume generated by the primary actors. System administrators use it to ensure the physical view has the necessary hardware to connect to the secondary actors. By aligning every specialized blueprint against the scenarios view, the use case diagram provides the constant reference point needed to keep a multidisciplinary design team in sync.